During this session, I'm going to be talking about AC generators as required by the IB Physics course, topic 12, electromagnetic induction. From the diagram above, we all know that there's not giant batteries attached to every house. They're normally attached to mains electricity, which comes from a national grid, which comes from a large generator of some sort, okay, which comes in a power station. So what we're going to look at is we're going to look at how these AC generators of all sizes work. So let's look at one close up to start with. Now this is a picture of an AC generator. What we can see here, let me describe the sections. We have a magnet with a clear magnetic field going from north to south. Inside that magnetic field I have a coil of rotated wire. Okay, now these each one of these pieces of wire is going to be laminated and covered in plastic, so they're separate coils. And what happens is, after having these coils, they're connected to what's known as slip rings, and these slip rings will rotate around and around and around, and they maintain a contact with the electric circuit through some carbon brushes. So that carbon brushes allows it to maintain contact. Now, as we know from EM induction, we can recognize that if we have some method for rotating this coil of wire, what's going to happen is the coil of wire is going to be moving through a magnetic field, which is going to induce electricity. So that's one thing. However, we've got to note here that as the coil of wire rotates around, the direction of the induced current is going to be changing, flipping back and forth, back and forth. So that's why we have an alternating current. Okay, it alternates direction. Now let's think about what's actually produced by a device like this. Okay, so we're ignoring about what we use to cause the rotation. We're just saying that rotation occurs. So what is created here? As the rotation goes about, what we can see here is the current fluctuates as the coil position changes. When the coil position is standing up and it's directly, I guess, perpendicular to the magnetic field, that means that no current, or the current will be zero for that moment in time. However, as it rotates down, and what we're seeing here is that the more the coil is passing through the magnetic field at this time, so the maximum area of the coil, which is going through the magnetic field, comes up at the next point. As it continues rotating around, we return to a point when it's standing upright. The coil is relatively upright, so we return to zero again. And as the coil continues around to 270 degrees, we get a maximum on the reverse current, and then as it returns to 360, it comes to the end of the cycle and returns to a current of zero. This rotation will carry on and on and on, and as we can see, that each time it rotates, it will go through this cycle. Now this is a sinusoidal cycle. That means it will keep on going, and it will follow that of a sine or cosine rule. Now, the EMF can be calculated from, and we know this, from Faraday's law. Okay. Now we also know that the magnetic flux is equal to the area multiplied by the magnetic field strength times cosine theta, the angle between the area and the magnetic field. Now, if we look at this more closely, we can see that it's very, very clear that because of that cosine theta, the shape of the curve is going to have to be sinusoidal. That's the driving feature. So dependent on the angle of the coil depends on the EMF which is being produced, and in turn the current. And we've got to recognize here that both the EMF and the current would be in phase with each other. So the greater the EMF, the greater the current. The less the EMF, the less the current. So the ways we could increase this, we can increase the number of turns on the coil. So that's increasing the value for N in Faraday's law. Increase the area of the coil, so that would be increasing the value for A inside the magnetic flux calculation. Using a stronger magnet, so increasing the value for B, the magnetic field strength. Rotating the coil faster, so that means that the velocity of the wire through the magnetic field is increased. Please note that the rotating of the coil faster will also increase the frequency. So the frequency of that sinusoidal curve will increase if the rotating coil is done any faster. And what we can see here, and this just kind of emphasizes, is our current and our voltage will go through a continued cycle. The terms we tend to use here is for that maximum voltage to be recognized as voltage O, and the maximum current to be IO. So those are the symbols which we use to show those maximum values. That gives you a quick introduction to an AC generator. And now in the future lessons we're going to look at how we can do some calculations with this alternating current. Now we can look at it and think about it with respect to considering how it would work in a circuit.